class today. I also want to remind you about there is a test coming up pretty soon, not that far. So we're on the, say the night right here, so we're looking, you can't really see it here, it's on the 6th, which is the Wednesday after spring break. And that'll probably cover chapters 3, 4, and 5, and then maybe even a little bit into the next chapter after that. But we'll see. We might just be 3, 4, and 5. But again, I know that sounds daunting, but 3 and 4 are really right together because you're going to use Ohm's law, you're going to use resistance, all that jazz in chapters 3 and 4. And y'all have covered that pretty well in lab. I know not all of you are in lab, but you have covered that in lab as well. I understand many of you have your midterms soon too, right, in lab, where you did resistors and combination circuits and all that business. So we'll be covering that again today as well. Have any questions? We want to remind you too that on the website, if you're wondering about sort of how your grade is going, you can look at the grade calculator, which is just a spreadsheet that gives you that allows you to calculate your average. So you can go on there and you can put in the grade for your exam 1, your exam 2, and then what you expect for exams 3 and 4, and the final, which remember is out of 150. And your class participation, which should right now be right about halfway, because we're about halfway through the semester, so it should be right around 25. I think I had some students that were 30 or a little more than 30. But if you're around 25-ish, give or take a few points, you should be good to go. All right? And that'll give you your average. There's still a lot of points left in the class, so even if you've done poorly in the first 2 exams, you can still do well in the class. Any questions about that? Yeah? All right, well, that's there for you. What's that? 4 and 5 are both pretty big chapters, yeah. But they will definitely, both of those will be on the next test for sure, as well as 3. Because we still have a while. The first test came really quickly, and then successively they get longer in between tests. Okay, so let's start with chapter 4, which is on DC circuits. We're going to do AC circuits too, but DC is a little simpler than AC. The difference between AC and DC, like a fan, AC, DC. All AC stands for alternating current. That means that's the type of current that we get out of our outlet. It means that the current goes back and forth between positive and negative values. And because it does that, it's a little more complicated to deal with, but we'll do that in a later chapter. But in this chapter, we're just going to deal with direct current circuits. That means that the current has a constant value, that it's always the same. First, we just want to define a few things. We talked about batteries being a source of voltage, but we want to think of them more in a sense of being a source of electromotive force. Are an ideal source of voltage. This is your battery will be something that will give your electrons energy as they move through it. We'll use this symbol for EMF. Script E, or it sort of looks like an epsilon. And we're going to sort of use it interchangeably with our voltage of our power supply, and you'll see me use both. But largely we want to distinguish between them because batteries and power supplies have an internal resistance R. And this causes a drop in potential or voltage. So we distinguish between the EMF and the voltage because if we imagine that we have a battery consists of an ideal source of electromotive force. That means that ideal source of electromotive force has no internal resistance. But a battery also has a source of resistance. And then the difference between V and our EMF is going to be that V takes into consideration the actual resistance of our battery, the internal resistance. So if I look at the terminal voltage, which is going to be this delta V here, then our delta V, our terminal voltage, is going to equal to our EMF minus the current times our internal resistance. So far we've assumed that this internal resistance is zero, as we've been doing in Chapter 3 with batteries and resistors in terms of Ohm's law. But this is never the case for real batteries, that you always have this internal resistance. It's because of this internal resistance that when you have a battery, I have this battery, and it consists of an EMF source and an internal resistance. When I run a current through this battery, powering whatever it is that I'm powering, this resistor causes what? A drop or a rise in potential. Does it cause your system to lose energy or gain energy? We see a drop in potential, right? I lose energy across that resistor. And when I have an internal resistance, that means that it's going to act like a sort of heater. Often when you send electricity, always when you send electricity through a resistor, you will lose thermal energy, that it'll heat up the resistor. You may have seen this in lab, right? Have you, any of y'all burned up resistors in lab? They start smoking or fizzling or whatever. It's okay if you've done it. I've done it too. It's because you run too much current through them and they exceed the safe capacity. They just start heating up and then they burn up. So this happens in a lot of your batteries. Like, what happens on your cell phone when your battery starts getting bad? What happens to it? Well, it dies, but what happens when you try to charge it? It gets hot, right? So when you have a rechargeable battery and you start to recharge it and it feels really warm, that means that it's close to the end of its life. And physically what's happened is the internal resistance of your battery has increased. Okay? And when you increase that internal resistance, you lose more energy across it when you run a current through it, like when you're charging your battery. Now let's try this little quick test. A battery has an ideal EMF source of 12 volts. Current of 4 amps through it. The actual potential is 10 volts. What is the internal resistance? So I'm losing a certain amount of potential through this internal resistance. What is the internal resistance? All right, about 5 more seconds. I'll stop at 45. 45. All right. Okay, good. B is the right answer. And I know that I start out with an ideal EMF of 12 volts. But it has an internal resistance across it. And if I measure my actual terminal voltage, measure it across these 2 points, this is going to be my delta V, and it's equal to 10 volts. That means if I have 12 volts here, I'm losing 2 volts across that resistor. Since I have a current of 4 amps, that 2 volts has to equal I times R. So 2 volts equals 4 amps times my internal resistance, so R is equal to 0.5 ohms rather, excuse me. So that's my internal resistance. You can see some multiple choice questions about internal resistance and just this idea that batteries, real batteries, do have a source of internal resistance. In fact, our houses have a source of internal resistance too. We'll talk about that later, but it's a little bit different than we see. Okay, so let's look at this circuit. We've already sort of thought about this, but we want to consider each part of this circuit has either a drop or a rise in potential. So we can list those: drop as a minus V or a rise as a plus V. I either lose energy when I go across a component of a circuit, or I gain energy when I go across a component of a circuit. So which of these, I have 2 resistors here and here, what do they experience? Do they experience a drop or a rise in potential, a plus or a minus V? I see a drop in both of these. So I have minus V here, minus V here. And then my battery sees a rise in potential. I always like to think about charges. As they move through the circuit, have a charge, it gains energy right here, And then as it goes through the circuit, it loses its energy in each of those resistors. And then it goes back to the beginning, gains energy in the battery, it goes through the resistors, loses energy in both of those. So the component that they gain energy in the batteries. The potential is a positive value. They lose energy in the resistors. And that the energy that they lose is equal to negative IR. So we'll see a potential drop that's equal to the current times the resistance in each of those. And then that energy generally goes into thermal energy for the resistors. But it can also go into mechanical energy if you're turning a motor, or you can also go into chemical energy as well. But we'll see that later. So each component has either a drop or a rise. This is E. This is minus I times little r. That's the potential across the internal resistance. And then this is going to be minus I times R. Now when you go around the entire circuit, the change in the potential is going to be 0. So if I imagine my circuit again, I have my little r, there's my big R. As I said, I get a positive E here, a minus IR here, and a minus IR here. When I go around the entire circuit, if I go around that whole loop, beginning here and going all throughout the circuit, then I can add up all those changes in potential. So I get a plus E, a minus I times little r, minus I times big R, and then that's going to equal to 0. That's just saying that an electron at a particular spot will have the same energy when it returns back to that spot. So an electron traveling through this circuit will have a certain amount of energy here. In fact, at this point, what is going to be the energy of the electron? Is it going to be positive, negative, or 0?
Negative.
Well, it's going to be 0, yeah. So you can't really have negative energy. But here we can have negative potential, so it's not really negative energy. Negative potential, remember, potential is energy per charge. So it has to do with the charge. So here I'm going to have 0 energy. I gain energy, all the energy that I'll ever gain, and then I lose that energy here and here. This is a pretty fundamental rule. This is called the loop rule, and we'll see it as we deal with circuits. But it's a pretty fundamental rule that electricians and electrical engineers and what have you use. And it just says that the potential across any loop is equal to 0. The sum of all the potentials across any loop is equal to 0. So given that, in this case, we could solve for the EMF. The EMF of the battery is going to be I times little r plus I times big R. And we'll apply the loop rule in that way in a lot of circuits as we move through this chapter to determine unknown currents or unknown voltages. Let's look at resistors in series. So just like we did for capacitors, remember with capacitors, we had capacitors in series, capacitors in parallel, and we had different rules for all those. And then we also had combination circuits with capacitors. So you'll see similar things on this next exam, where you have to deal with resistors in series, resistors in parallel, probably just in like a multiple choice question, because those are fairly straightforward. But then you'll also have combination circuits, and then we'll have multi-loop circuits, which will be a little more complicated and dealt with slightly differently. I'm going to go ahead and give you all the rules. So just like we had for capacitors in series and parallel, we have rules for resistors in series and parallel. So let me just go and lay them all out for you, but then I'm going to represent them as we go through these. But let me just go ahead and lay them out for you here. So for resistors in series and for resistors in parallel, I have some rules. The first is the equivalent resistance. For resistors in series, this is R1 plus R2 plus however many resistors I have. For resistors in parallel, the equivalent resistance is 1 over R1 plus 1 over R2 plus whatever I have. Now be careful, because these are switched from what they were for capacitors. If you remember for capacitors, this type of expression, the inverse, the sum of the inverses, was for series. So these two are switched from what they were with capacitors. For series circuits, they all have the same current. The resistors have the same current. That is, I1 equals I2 equals I3 equals however many resistors you have. For parallel circuits, the resistors have the same voltage. V1 equals V2 equals V3. That's however many I have. This was the same for capacitors in parallel, and we can think of these as resistors in parallel being hooked up all to the same battery. The third rule, is it the sum of the voltages, the total voltage, is equal to V1 plus V2 plus V3 plus however many we have. We had that for capacitors as well. If I had two capacitors in series, their voltages had to add up. For parallel, the total current is equal to I1 plus I2 plus I3 plus however many I have. This is called the junction rule, which we'll identify that later. And then for both of these, we have V equals IR. So Ohm's law. So those are the sets of rules. They're similar in some ways to what we have for capacitors, and I'll explain them more as we go through them, but just to sort of lay them all out there so that you see them. You'll need to know these rules for these different circuits and then know how to apply them. But the rules in themselves are pretty simple. It's just when you approach circuits, you'll need to have those in mind as you work through the circuits. Okay? All right, so do what you need to do to memorize those. Put them on a note card, flashcards, whatever you need to do. Okay, so let's look at resistors in series. Resistors in series, just like we had for capacitors in series, you identify when the resistors are in series because there are no breaks in the circuit. You have no junctions. And so these are clearly in series because there are no junctions anywhere on the circuit. And even if I were to put a resistor here, those would still be in series. Just because I have a bend in the circuit doesn't necessarily mean I have a junction. I know that's sometimes confusing. It was confusing on the exam I took, that sometimes I have capacitors or some device that just make a bend, but that doesn't mean that they're in parallel. That just means they're still in series. Okay? So resistors in series look like this. There are no junctions. We've already said that the change in potential across the battery, this delta V, has to equal IR1 plus IR2. This goes back to that loop rule, right? I have a positive potential here, negative IR1, negative IR2. The sum of those all have to equal to 0. So I get this expression. That is to say that I can, because resistors in series have the same current, so this current that comes through this circuit goes through this resistor. It also goes through this resistor. It doesn't have anywhere else to go, right? It has to go through those resistors. So that's where this rule comes about, that the resistors in series have the same current. They have to have the same current because there are no junctions for that current to split up into. So because of that, I can take out this I and write this expression like this. So because of this expression, I can say for resistors in series that my equivalent resistance is equal to this term. So for series resistors, the equivalent resistance is equal to R1 plus R2. All right, so we see a couple rules already. Actually, I think we see all three. We see the equivalent resistance. Resistors have the same current. And then this, the third rule, is really just that loop rule restated. That the total voltage, that is the voltage here, equals the sum of the individual voltages, which is the same for capacitors. Also, just want to point out, this should be obvious. I hate to even say it, but it won't be obvious when we deal with resistors in parallel. But the equivalent resistance is always bigger than any individual resistor. So R equivalent is bigger than R1, R equivalent is bigger than R2. It's the sum, right? It has to be bigger than the individual resistors. But we'll see with resistors in parallel that's not true, that the equivalent resistance is smaller than the smallest resistance. Okay, so that's why I pointed out there. The equivalent resistance is always bigger than any individual resistor. All right, so just to formalize those rules, I've already stated them, but resistors in series have the same, gosh, what do they have the same of? Same current, voltage, or what? They have the same current. They have to have the same current. So resistors in series have the same current. And then also the loop rule. Remember, the loop rule just says delta V across any loop equals to 0. Says that the change in potential across the resistors in series adds to equal the change in potential across the battery. All right, so that is to say delta V across the battery is equal to IR1 plus IR2 plus however many resistors I have. All right, so let's look at these two light bulbs. They're hooked up in series. First of all, if I just remove R2, what's going to happen? If I take out this light bulb, y'all do this in my little Christmas lights? And the batteries? Yeah, that was pretty fun. Was it fun? I know for some of you it didn't work very well, but others thought it was kind of cool. Did y'all think it was cool? Right. Huh? Yeah, that was a problem. But it was only in one class. Yeah, that's really. So if I have these two light bulbs that are hooked up in series, what happens if I just take one of these out? Like if I take this light bulb out, what happens to the other one? Well, at first it's just going to go out, right? Because I've broken the circuit. So if I do take out R2 and, is that okay, Desiree? Can I go to, yeah. So if I take out R2, R1 goes out. Because I just have a broken circuit, right? The current comes along here. If I take out this one, that means that the current can no longer go through that filament in the bulb. But if I replace it with a wire, what's physically going to happen, I mean, you said that R1 becomes brighter, and that is true. So the first light bulb becomes brighter. But it becomes brighter for these reasons. First, if I take out R2, the R equivalent, the equivalent resistance, if I remove R2, what's going to happen to the equivalent? Will it go up or down? Right, the equivalent resistance will go down. And remember, V equals IR. So if R goes down, V is constant because it's just whatever your power supply is. If R goes down, that means I goes up. So my current is going to increase. And then the voltage across the second light bulb will increase. Okay? Because V is equal to IR, V2 then is equal to I times R2. So if I goes up, then V2 has to go up. You can also think of this in terms of, well, gosh, if I have 12 volts, when R2 is in, I get 6 volts and 6 volts, right? It splits them up. But if I take out that R2, now I'm going to get 12 volts if this light bulb is no longer there. So I have more energy going into that light bulb, so it'll be brighter. All right, let's do an example. Let's say I have a 1, a 2, and a 2 ohm resistor in series. I want to know what is the equivalent resistance, what is the current through the resistor R1, what is the potential across each resistor, and then what is the voltage across yeah, what is the potential or the voltage across each of those individual resistors? It'll just take a minute. I'll give you a head start, and I'll jump in there. But find the equivalent resistance, find the current through the equivalent resistance, and then find the voltage across each of those resistors. All right, my equivalent resistance is what? It's equal to 5. I just say 1 plus 2 plus 2 is equal to 5 ohms. And then I want to find the current. So if I redraw that, I have 10 volts, 5 ohms. What is this current? It's going to be equal to 2. So I1 is V over R. That's going to be equal to 10 volts over the equivalent resistance, which is going to be 2 amps. Notice I'm looking for I1 here, but I didn't use I1. I didn't say 10 volts over, what was this, 1 ohm or whatever, because the current through a series circuit is limited by the equivalent resistance, not by any of the individual resistors. Just make a note of that. So note, don't use R1, but use R equivalent. You can think of charges coming along through this circuit. They're going to be limited in their way that they flow, not by this resistor, or by this resistor, or by this one, even though they come to this one first. But they're going to see all 3 resistors at the same time. And so they're going to be limited by the total resistance of that circuit. All right, and then we want to know the voltage. Remember that resistors in series all have the same current. That's one of our rules. Resistors in series have the same current. Resistors in parallel instead have the same what? They have the same voltage, right. It's as if they're all hooked up to the same battery. And so since resistors in series have the same current, then we can find the voltage across each just by using that current. IR1, IR2, IR3. That's going to be 2 amps times 1 ohm, 2 amps times 2 ohms, and 2 amps times 2 ohms. It's equal to 2, 4, and 4 volts. Notice here that when I want to know the voltage across an individual resistor, I do use that resistance. Unlike up here, when I wanted the current to an individual resistance, I have to consider the equivalent resistance. I wouldn't even really think about the current through an individual resistor. Instead, think about finding what is the total current through these resistors in series, and then recognizing that that current is the same for all of them. Also notice here, one of our rules, that 2 plus 4 plus 4 has to equal 10 volts. And 10 volts was the voltage across our battery. That's the loop rule, that the voltage across the battery is equal to the sum of the voltage drops across the resistors. That the sum of all the voltages is equal to 0. So the sum of all the voltages across a loop is equal to 0. That's called the loop rule. Okay, so that one's fairly straightforward, I think. Probably not going to, you're not going to see a free response that's just series or parallel. You will see a free response almost certainly that is a combination circuit, which we'll do later. But before we do that, let's do parallel. Oh, let's see. Recall that the change in voltage across the resistors in series adds to equal the change in voltage across the battery. So if you know the voltage across the first two resistors, then you can find V3 by subtracting the voltage across the battery minus, or rather, subtracting from the voltage across the battery V1 and V2. So I'd say 10 volts minus 2 volts minus 4 volts, and that's 10 minus 6, or 4 volts, and then that would give me V3. Notice if you're pretty good at this, kind of like with the capacitors, you could look at this and look at the distributions and notice that I have a voltage here across a 1 ohm resistor, across a 2 ohm and a 2 ohm. The voltage across this resistor has to be half that of this resistor. Notice that's a little bit different than it was with capacitors. Remember, with capacitors, Q is equal to CV, so if C was big, that means V was small. But with resistors, V is equal to IR. So if R is big, that means V is big. So our big resistors will have a big voltage, and that was different for capacitors. So I have a small voltage here, big voltage by a factor of 2. Excuse me. The only numbers that can do that are 2, 4, and 4. That will add up equal to 10. Okay? Does it sit well with y'all, okay? Hopefully it does right now. If not, come see me. I can help you with these. You really need to get these circuits now with the resistors. All right, let's try this clicker question. What is the potential across the 8 ohm resistor? 4, 8, and 12 ohms. 4, 8, and 12 ohm resistors in series with a 12 volt battery. You need to follow the same process. You need to find the equivalent resistance, find the total current, and then find the voltages across those 3 resistors, although really we just want the voltage across this resistor. Doing really well. We'll do about 10 more seconds. Stop at 1 minute. Okay, awesome. B is right. I have 4 volts. My equivalent here is equal to 24 ohms. So my current is equal to 12 volts over 24 ohms. That's 0.5 amps. So if I have 0.5 amps across this resistor, that means I have a voltage equal to IR, or 0.5 times 8, which is equal to 4 volts. So B is the right answer. Notice, too, that I can pretty quickly figure out the voltage across the 4 ohm resistor. Just given this answer that I have 4 volts here, what is the voltage across the 4 ohm resistor, which has half the resistance? It has to be 2. And then across this resistor, which is 1.5 times the 8 ohm resistor, it has to be 6 volts, right? So I have 2 volts, 4 volts, and 6 volts, and notice those all add up equal to 12. So you'll see with this that you're looking at proportions really, and if you have a combination circuit, it'll become pretty easy in the end to look at it and see how everything's laid out. Okay? All right. But it takes practice. It takes lots of practice to really see these in your mind. All right, let's look at resistors in parallel. This is probably the easier of the two, because resistors in parallel, the potential difference across each resistor is the same. And this is likewise for capacitors. Remember, we have the same rule. That is that V1 is equal to V2 is equal to V3 is equal to whatever, however many resistors I have. And then also recognize that the resistors are independent of one another when they're in parallel. Likewise, they work for capacitors. So if I take out a resistor, it doesn't affect any of the other resistors that are in parallel. They're completely independent of one another. Also, the current entering a junction must equal the total current leaving a junction. And this is called the junction rule. We use this quite a bit when we get into multi-loop circuits, but we'll use it here as well, the junction rule. And it's just based on the conservation of charge, that if I have a current coming into a junction, say, I don't know, let's say my current here is 8 amps. If I have a current here that is 5 amps, then that tells me I must have a current here that is 3 amps, right? So pretty simple idea, but it has to be true that the current coming into my junction always equals the current leaving that junction, because I can't just lose current. It has to be going somewhere. So looking at this circuit, I would pick a junction. I have a current I coming into it. I have currents I1 and I2 leaving that junction. Over here, I would write it a little bit differently. I would say I1 plus I2 is equal to I. But those are applications of the junction rule, that the incoming current equals the outgoing current. To find the equivalent resistance for these, you do that 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors you have. And remember, you'll have common numbers. So like if I have 1 over a third plus a sixth, that's equal to 2. 1 over a quarter plus a quarter, that's equal to 2. 1 over a half plus a half, that's equal to 1. And we had other combinations. In fact, I feel really bad because like that capacitor circuit, it was supposed to work out more evenly. I'm really, really sorry about that. I graded it very lightly. Well, I'll tell you more about that later. It was meant to be easier than it was. But some of you still did get it exactly right, so I was really proud of you for that. And then a lot of you actually did get the right proportions right, and I didn't count off that much if that was the case. So, all right? Yes, sir. I don't really have to ask you for forgiveness. All right, I mean, you should have been able to do it. Many of you were able to do it, and so I was glad for that. But I meant it to be a little easier. Okay, so what happens to the equivalent resistance as you add resistors? So what happens to this expression as I add additional resistors to it? Did you guys hear about that Italian chef that died? Yeah, he passed away. All right, just a few more seconds. I'll stop at 43. Okay, B is right. The equivalent resistance decreases. If you don't believe me, just put in some numbers, right? 1 over a third plus a third would be 1.5, right? 1 over 2/3 is 3/2. 1 over a third plus a third plus a third would be 1. So as I add additional resistors, my equivalent decreases. I like to think of it as if I have a circuit with resistors in parallel, I have an electron that comes along up here, and it comes to this point, and it sees 2 possible places to go, right? And so 2 possible places to go is harder. It offers more resistance than if I have 3 possible places to go. So now it comes along here, and it says, I don't have 2 ways to go. Now I have 3 places I can pick from. That's a lot easier than just having 2 places. So as I add more resistors, my equivalent will actually decrease. And that's sort of counterintuitive, but it's true for resistors in parallel, that the equivalent resistance will decrease when you add resistors. And then also is true is that the equivalent resistance is always less than the smallest resistor, or smaller than the smallest resistor. So if I have, 100 ohms, 50 ohms, and 2 ohms, then the equivalent resistance will be less than 2 ohms. That your equivalent resistance is always less than your smallest resistor. If you already just put in the numbers, you'll find that it is less than 2 ohms. It's smaller than the smallest resistor. All right, let's do an example. So let's say I have this circuit. I want to know a couple things about it. I want to know the currents and voltages for each resistor and the total current and the equivalent resistance. So go ahead and try that out. Not a particular order for you to work this. There are a couple different ways to do it. But think about what are the voltages and the currents. I'll give you a minute to work through that. All right, so fairly straightforward with parallel circuits. I have 10 volts here and 10 volts here. The voltages across the battery or across the resistors are always going to be the same as the total voltage or the source voltage across this parallel branch. So as we did with capacitors, we will think about, well, I have a total of 10 volts across these resistors. So I have 10 volts across each one because they're in parallel. And then I know the voltage and the resistance for each of these. So I can find I1 is going to be V1 over R1, which is going to be 10 over 2, or 5 amps. Similarly, I can find I2 is going to be 10 over 4, which is, what's that? 5 halves, 2.5 amps. Okay, so that's my current through each of those resistors. V1 and V2 are both 10. Because they're in parallel, they have the same as the battery. That's one of our rules. Then our equivalent resistance is 1 over 2 plus 1 over 4. See, that's 2/4 plus 1/4 is 3/4, so that's 4/3 ohms. And I can find my total current I, which is this current. I can do that in a couple different ways. I can say that the total current is equal to V over R equivalent. That's going to be 10 volts over 4/3. That's 30 over 4, 7.5 amps. 7.5. All right, so that's my total current. Or I can also look at these two currents and say that my I is equal to I1 plus I2. This is probably the easier way. And say that that's 5 plus 2.5, which is 7.5 amps. So either one of those ways is appropriate. All right. There are some checks, just like we had with capacitor circuits. If I find a total current, I need to make darn sure that it's equal to the sum of all my currents. And let's see what we got here. Let's do this clicker question. What happens to the voltage in each resistor when you add resistors in parallel? What happens to the voltage in each resistor when you add resistors in parallel? I'll stop at 28. Okay, awesome. C is the right answer. The voltage will stay the same because those resistors are completely independent of one another. So whatever, like if I have 10 volts here, I'll have 10 volts here, 10 volts here, 10 volts here. As many resistors as I want to add, I'll still have that same resistance. Let's see, do you know how you get a baby astronaut to sleep? You rock it. Okay. Now, what happens to the total current? So as I add resistors in parallel, this is the total current. What happens to that total current? Does it increase, decrease, or stay the same? Keep those same options, A, B, C, or D, or A, B, or C. Does the total current increase, decrease, or stay the same as I add resistors in parallel? As I add more and more resistors, what happens to that total current? Yeah, what happens to the total current when you add resistors in parallel? So what happens to the total current as you add resistors in parallel? All right. I'll stop at 105. 105. And we'll stop with this one. Back to your exam. The total current will increase. Remember one of our rules, which is the junction rule, which says that the total current, I, is equal to the sum of these individual currents. I1 plus I2 plus I3 plus however many I have. So as I add more and more resistors, I'm adding more and more terms to this, which causes my total current, which is the current here in the circuit, to increase. That happens in your household too, by the way. Your house is laid out as a parallel circuit. As you add more and more devices to the individual circuit, it causes that total current to go up, which is why your circuit breaker kicks off. And we'll talk about that later at the end of this chapter. For now, let me hand back your exams. Are we get at 820 or 825? Okay, I'll go ahead and hand back your exams. Do just want to point out that the exams, the solution, I posted it yesterday on the website, so you can find the multiple choice answers, though I marked actually on your exams if you got the multiple choice correct or not. And then there's also a video with the solution. And I also want to remind you that the multiple choice was worth 20 points. The free response was worth, what, 70 points? Yeah, 70 points. And then that derivation that I did in class the other day, that was worth 10 points. Okay? All right. Well, y'all just probably you need to go. I want to remind